All right, so here's our walkthrough for Lab 5, which develops our understanding of probability distributions and gets us comfortable with working with them so that we can use them more later on. So for this lab, you're going to want to download these two files, these PNG files. They're images from the textbook that I'm using because they're good problems to work on. And so if we download these all to the same folder, just like we usually do, when you open them up in the lab, so open up the lab problem. It'll actually import the video where I have a little bit of code that, it'll import the image, not the video. So I have some code here that lists this image file and it puts it right here. And it'll also knit it together, which is nice. So that's what we need for this lab to get started. Basically two problems in the textbook we're going to work on in detail. So, yeah. Let's start with answering the questions for this question on cat weights. Okay, here's a histogram. It's got the body weight of different cats. So between 2 and 2.25, we got 29 cats. 2.25 and 2.5 is 32 cats. So if we're wanting to know what fraction of cats weigh less than 2.5, well, that would include these two categories. So to answer question A, we could say Control Alt Insert to get my little calculator. I would say 29 plus 32 are the cats that are less than 2.5 pounds. And I got to divide by the total. I don't know. I could add up all these values here to get the total. Or I could see up here there's 47 female and 97 male. So 47 plus 97. I can do it all at once. That tells me what fraction of cats weigh less than 2.5. So about 42%. 42.6%, if I want to write it as a percent. So you could answer the rest of the questions, 2.5 and 2.75, 2.75 and 3.5. That would be these three categories. And then, so try to do the rest of these your own, and you could even try to do the next one on your own as well, and only use the video if needed. But if you are stuck after pausing it and trying to figure it out, here is at least a start on it. So if we look at this histogram, it's actually a table which presents a histogram for us. So A says just describe the distribution. Well, I could say it looks like it's fairly symmetric. These numbers are smaller, but maybe it seems a little bit right skewed if I'm seeing these numbers towards the right are bigger. So I would say a little bit right skew, meaning more data lies to the right of the peak. Here's our peak. Looks like 35, most common income range. We got these different income ranges. It looks like 35 to 50,000 is 21%. That's the biggest number. 35K to 50K. So that's kind of general terms, what's going on with the distribution. And this distribution is easy to calculate probabilities because if I want to find the probability in a given group, it's already given me a percentage. So I could just convert that into a probability. So what's the probability that someone makes less than 50,000? So that's part B. 50,000 corresponds, I'm going to annotate this. 50,000 is less than this value here. So I'm looking at all these here. So to find that, my annotations, I'll clear them. Okay, to find that, I'm gonna have to add up all those percentages. So 2.2 plus 4.7 plus 15.8 plus 18.3 plus 21.2. That'll give me a percent. So I have to divide that by 100 to get a probability. There we go. Does that look good? Yeah. So 0.62, a little over 0.5% of people, half of people make what? Less than 50,000. So here we go. What's the probability? Part C is adding another dimension to this. We know the percentage of male and female. So 59 male, 41% female. It's a little bit more skewed to males working in this sample. What's the income? What's the probability that a randomly chosen resident makes less than 50,000 and is female? So if we want to find that, here we go. We got this joint probability. Probability that less than 50,000 and female, since they might be related, we would really have to use this formula here. Probability less than 50,000 and female is the conditional probability times the probability of female. Remember this formula, probability of A given B is, I'll say it this way, A and B equals probability of A given B times probability of B. That's the formula that we're using when things are not independent or dependent. Okay, but we're going to use the independent formula just to find this. Probability of male and female, A and B, is probability of A times probability of B. We're just going to multiply them. So probability of being female was 41%, 0.41. Probability of making less than 50,000 is this here. So we're going to multiply those. And this only works if they're independent. Sometimes we assume it's independent, and it works. Okay, I'm going to pause this just a second. Hello, this is Paul. Okay, sorry, spam caller. I guess I didn't pause the video, but okay. So continuing, if they are independent, we're gonna just multiply the two values to see that. Okay, about a quarter of people, 25%, I'll say 5%. What was the question C? I have to refer to this again. Making less than 50,000 and being female. Okay, so then we're going to compare this to something that D tells us. D says, actually, if we look at the percentage of females that make less than 50,000, it's 71% of females make less than 50,000. So we can do some comparisons here. The probability of being less than 50,000 and female, if they are dependent, we have to use a different formula. Probability being female and making less than 50,000 was just given. If you're female, there's a 71.8% chance of being less than 50,000. So this number right here is actually 0.718, 71.8%. Yes. And we're going to have to multiply that by the probability of being female, which was 41%. Okay, so if I find this probability, if they're independent, it should be the same as my previous calculation. But since they're not, this shows they're not independent. We just showed something that the joint probabilities are not what you would get if you assume they're independent. So since this is different, it's different than what we assumed in C. So we assumed independence in C. The distribution is independent of gender, dependent of gender. We assume that, but we got a different value. So this is evidence that gender and income are dependent. Female are more likely to make less from this data set. It's an interesting result. So that's what we find from this question. So this is kind of analysis you can make now with conditional probabilities. Put that information together in an interesting way. Okay, so last part, we're looking at just what are probability distributions. I think we'll cover this in class. The main thing is that a function always has probability distribution is something that always has a value that's between 0 and 1, and if I add up all the possible outcomes, they equal 1. So considering this, the two probabilities are between 0 and 1, and if we add them together, they equal 1. So this is effectively a probability distribution. It's a probability distribution that we can model using a probability density function, P of x. Okay, so we have some more examples that you can test, whether these are probability density functions or not. And for problem 5, I've plotted the income into a distribution. And if you want to see from this distribution, there's this variable probability. Here's a hint. If you want to figure out what those probabilities are, insert, that's not what I want to do. Insert, if you say probability, it gives you a list of all those. So you can see, are they between 0 and 1? And if you want to know what is the sum of those, that result can help you answer number 5. Okay, so here's some more examples. Again, you have a probability vector that you can look at. Here's the histogram of it. If you want to analyze that vector probability, it looks like this. And to get some more information on it, you might want to say sum of, sum of probability. So I'll give you some more information on what your distribution looks like. Okay, that's all my tips for this lab. We'll see you in class for any questions you have, and I'll get to recording the next one. See ya.